Hey class, welcome to Math is Fundamental. Today we're going to be doing section 5.17, part 1 of AP Stats. We're going to be looking at sampling distribution models, specifically with means. So let's get started. So we're going to do a little review of some terminology here. So what a statistic is to a sample, a parameter is to a population. So in this case, we're going to be talking about the mean. So if you have data from a sample and you find the mean, then that mean is a statistic. If you have the entire data for the whole population and you find the mean, that mean is called a parameter. And the observed value of a statistic typically varies from sample to sample. So if we think about it, if we take a sample from the population and we find the mean, and then we take a different sample from the population and we find the mean, it's not going to be exactly the same. I mean, there's a chance it'll be the same, but there's a large chance that it won't be the same. And if we take another sample, it might be different. And those are just going to vary. This is just called sampling variability. And it's just what happens when we randomly select a sample. There's not really anything you can do to control from this. So really the best thing you can do is just take as many samples as you possibly can. So a sampling distribution is the distribution of a statistic, so sample mean or sample proportion. Today we're going to be doing sample means for every possible outcome. So this is called the sampling distribution. Now, this is kind of theoretical. I mean, we would have to take every possible sample from the population and get the distributions of all the means, for example, from every possible sample from the population. We're not going to do that in real life. So this is more of a theoretical idea. So it's a theoretical distribution of all possible sample results from a specific sample size, and N is the letter we use for sample sizes. So in class, I usually do this activity with my students, so I'll just try to describe it for you. Each student gets a paper bag with 10 slips of paper, and each one has a number on it, and each slip is the same size, and they're each folded, I think, in half just once. And so they have all these numbers. And then the student shakes the bag vigorously, pulls out 2 slips of paper, records the mean on their paper, and then puts the 2 slips back in the bag. And they keep shaking it, and they keep pulling out 2 slips of paper, recording the mean of those 2 items, putting it back in the bag. So for example, so N equals 2, because our sample size, we're taking 2 slips of paper out each time. We usually do the whole class, and so if I combine all the samples, I end up with something like 160 samples of a mean from each sample. And our mean of the sample means, so mu sub x bar is like each mean that you get. So every time you take 2 slips out of the bag and you record the mean, that's a sample mean, so that's x bar. And then if I take the mean of all of those means, the mean of the means, we ended up getting 10.23. So from all the students, all their samples, taking the mean of all of those, we get that. And our standard deviation of all the means, all the sample means, was 2.4. Now we did another one where instead of pulling out 2 slips of paper, we pulled out 4 slips of paper each time. So N is 4. We still had 160 samples. The students still shook the bag, took out 4 slips of paper, calculated the mean, wrote the mean down on their papers, put them back, shake the bag, pull out 4 more, and so forth. Mu of x bar in this case, so the mean of the means, was 10.86, and standard deviation of the means was 1.33. And if we calculate the actual mean of these numbers, so if we take our calculator, and I'm just going to use a graphing calculator here, 6 plus 7 plus 8 plus 10 plus 11, 12, 12, 13, 15, and 16, and we divide that, so the sum is 110, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers. So if I divide that by 10, I get 11 is the true mean. So what you can see here in this example is a couple things. We actually got pretty close to the true mean just by taking out 2 pieces of paper and finding the mean of those 2 because we had enough samples. But as we increased our sample size to 4 instead of 2, we got even closer to the true mean. And the standard deviation got less. So our sample means and the mean, so our sample means became more consistent as well, and closer to the true mean, or at least closer to 10.86. So just a couple things. It was a really cool activity that my students get to do if they were in class, but right now we're in a pandemic and my students are online. So that is what it is. All right. Properties of the sample distribution of a sample mean. So the mean of the sampling distribution of X bar, so mu of X bar, it equals mu. And mu itself is the parameter. So it's the population mean. So let's just write up here, note mu equals the population mean. Oops, that's a little sloppy. Mean. So what this means, we have a lot of means going on today. The mean of the sampling distribution, which is mu of X bar. So the sampling distribution of X bar. So the mean of all of those means equals the population mean in the long run. So the sampling distribution, actually, we don't even have to say in the long run. So the sampling distribution, remember, is the theoretical model where we would take all possible samples. So if we took all possible samples from that activity, every single one of them, and found the means, it would equal 11, period. Now, we don't take all possible samples in real life. We can't, or at least we're not going to, because it would take forever. So we can get close to the real mean the more samples we take. And then the standard deviation of our sampling distribution, so sigma of X bar is going to equal the true standard deviation of the population divided by the square root of n. So that's the population standard deviation divided by the square root of n. And these two things are on your formula sheet for AP Stats. You can find them here where it says sampling distribution for means. It's labeled really nicely for one population X bar, and you can see those formulas right there. Fun fact, a sampling distribution of X bar is approximately normal. So remember back to normal distributions with z-scores and all that stuff. If the sample size is at least 30, so n has to be greater than or equal to 30. If this is true, even if the population standard deviation, or even if the population distribution is skewed, we will have an approximately normal sampling distribution, which means we can use z-scores to find probabilities and things like that. This property is based on a calculus concept called the central limit theorem. So for those calc students in here, that should ring a bell. And if you haven't taken calculus, it's okay. You don't actually need to know the theorem. All right, now we have conditions that need to be met before we can do sampling distributions. So the first one is we need an independence. So the sampled values must be independent of each other. If this condition assumption is not given, then we can justify its existence based on context. So if it's clear from the context that we have independence, or we can use the 10% rule. So we talked about that before. And that's 10% rules. If the sample size is less than 10% of the population, we can assume independence. Randomization assumption, the data values must be sampled randomly. So they have to be sampled randomly or selected randomly or subjects assigned randomly to treatments. If this condition or assumption is not explicitly given, then we assume the sampling method was not biased and that the data is representative of the population of interest. So what that means is we can't just say, we're going to assume that the data was sampled randomly. You can't actually assume that because you don't know that. But you can say, you know what, I'm going to assume this wasn't biased. However they did it, it wasn't done bias or with any bias, and that our data is representative of the population, which is what a random sample would have been kind of hinting towards giving us. So that's only if they don't tell you explicitly in the problem that it's randomly selected. If they tell you, then you just say that it's stated in the problem. All right, and then the third condition is the approximately normal condition. The sampling distribution of X bar must be approximately normal. If this condition or assumption is not explicitly given, then verify that the sample size is large enough, so n is at least 30, to make this assumption. Note, if it is known that the population has a normal distribution, then you can assume any sampling distribution drawn from the population is also normal. So that's kind of another way to get there. All right. So our first real example here. A soft drink bottler claims that on average, cans contain 12 ounces of soda. Let X denote the actual volume of soda in a randomly selected can. Suppose that X is normally distributed with a standard deviation of 0.16 ounces. So it's stated that the population distribution of volume is normally distributed, which is nice. Part A is going to be review. So this is just if we are selecting one randomly selected can, we want to know the volume that it's at least 12.2 ounces. So we know that it's normal. I would suggest always drawing a normal curve. So make a picture, make a picture, make a picture. It's super important. And let's see, we've got 12 ounces here, standard deviation. So our mean, I guess our mean is 12. Standard deviation is 0.16. So if I want at least 12.2, and at least means that or more, this would be what my picture looks like. I can find my z-score at 12.2 minus 12 divided by 0.16 over the square root of 1. And we get 1.25. So the probability that X is at least 12.2, or the probability that Z is at least 1.25. You can write it either way. You don't need to write both. And then we would use our Z-score table. So, or you can use the calculator functions, but if you want full credit on any test, AP exam or my test, you have to label your inputs for the calculator function. So you might as well just use your table. It's easier. So 1.25, we go 1.2, and then all the way over to 5, we get 0.8944. And if you notice, so that's this probability, 0.8944, because the probability from your z-table always goes that direction. So we want 1 minus 0.8944, which 1 minus 0.8944, oops, it helps if I turn on my calculator, 0.1056, 0.1056, or approximately 10.56%. Okay. Now, what's the probability that 16 randomly selected cans have a mean soda volume of at least 12.2 ounces? So this is different. This is our new sampling distribution problem. We have multiple cans, so 16 randomly selected cans, and we're finding the mean of all of those ounces from that sample and seeing if that mean is, what's the probability that that mean is at least 12.2 ounces. So our three conditions: is it reasonable to assume cans are independent? Well, yeah. The ounces in one can isn't going to affect the ounces in the other cans. So it's reasonable by context alone to assume that the cans are independent. It is stated that the cans were randomly selected. So we would say stated that the cans are randomly selected. And our sampling distribution of X bar is normal since it is stated that the population distribution above was normal. All right, so now I can do my calculations. So Z is going to be 12.2, 12.2 minus 12 divided by 0.16, but this time our sample size is 16, not 1. So divided by the square root of 16. And then this equals 5. Think about what that means. Before, we were only 1.25 standard deviations away from the mean when it was just one can. I mean, yeah, you're over a standard deviation away from the mean, but it's not crazy far away from the mean. It's only 1.2 standard deviations. Now, if we take 16 randomly selected cans, the mean of those cans being 12.2 ounces or more, that's 5 standard deviations away from the mean. That's so much less likely to happen. So if we draw that, so here's my 12, and this time I'm 1, 2, 3, 4, 5 standard deviations from my mean. It's like this. There's my 12.2 this time. So because my standard deviation isn't just 0.16, it's 0.16 divided by the square root of 16. So the probability that X bar, my mean, not just X, but X bar, my sample mean is at least 12.2, is going to be the same as the probability that Z is at least or greater than or equal to 5. And that's just approximately 0. I mean, you can plug it in your calculator, but it's just going to be really, really, really small. If you want to plug it in your calculator just to see, you would go to second and then the distribution button, go to normal CDF. My lower would be 5 and my upper would be some really big number like 10, 100 million or something. 0, 1, paste, and my answer is 2.87 times 10 to the negative 7th power. So this probability of X bar greater than or equal to 12.2 is 2.87 times 10 to the negative 7th power. So 0.000000287. So saying it's approximately 0 is just fine. All right, and if you do that, if you write what I just wrote, the 2.87 times 10 to the negative 7th, then you have to write your calculator function. I know I didn't write it down. I actually wouldn't write this at all. But obviously that number didn't come from the table, which means you're using your calculator. You have to write the function down on the paper and label your inputs. Or just don't write it and say it's approximately 0. Now compare the two probabilities, explain why the observed difference exists. So the probability for 2A is relatively much larger than the probability for 2B since it is far more likely to obtain one can that has a volume of at least 1.2 standard deviations above the mean than obtaining a sample of 16 cans that has a sample mean of at least 1.25 standard deviations above the mean. And then this 1.25 standard deviations above the mean, it gets a little tricky because now my new standard deviation of my sampling distribution isn't 0.16 anymore. So we're not actually 1.25 standard deviations above the mean. So I'm actually going to change that. You're actually 5 standard deviations above the mean at that point, which is crazy. So really, really rare. All right, predict which is greater. The probability A randomly selected can has a volume between 11.92 and 12.08. So only 0.08 ounces above or below our true mean of 12 ounces, or the probability that 16 randomly selected cans have a mean volume of between 11.92 and 12.08 ounces. So if we think about it, they're giving us a little bit of a different situation this time. They're telling us we're going to be pretty close to the true mean and on either side. So which one, either one can or 16 cans in finding the mean, is going to have a larger percentage between those two pieces, close to 12? Well, I would predict that 16 cans having a sample mean within a half a standard deviation from the mean is more likely to occur than a single can being within half a standard deviation from the mean because we have a greater sample size. So it's more likely that we're closer to the mean. We have 16 instead of 1. And that will more consistently reflect the population mean. It'll yield data with less variability. So, and less variability, that's because our standard deviation is literally lower. It's 0.16 divided by the square root of 16. That is smaller. So we have less variability. Now, let's verify. It said explain and verify. So my z-score would be 11.92 minus 12 divided by 0.16 over the square root of 1. And this is negative 0.5. My z-score so this was for 11.92. So z sub 1, z sub 2 would be 12.08 minus 12 divided by 0.16 over the square root of 1. And that equals 0.5. And then here, so I'm within 1 standard deviation above and below. And And I can find the probability if I'd like, the probability that my z-score is between those two things, or you can write the probability that x is between 11.92 and 12.08. This equals 0.38. Now, if we have 16, z sub 1 is going to be 11.92 minus 12 divided by 0.16 divided by the square root of 16. This is -2. So now I am 2 standard deviations below the mean. And my z sub 2 for 12.08 minus 12 over 0.16 over the square root of 16 is going to be +2. So now I want the probability that z is within -2 to 2 standard deviations away from our mean. That's a lot larger of our curve. So we have a lot more probability. This is going to be 0.954. So we went from 38% to 95% probability. So my assumption or my prediction was correct. Now, if you're one of my students, there's one more page of notes. It's just another example for this. So maybe you can try it on your own and then check with our calendar, fill it in, make sure you get it done before class. Right? And that's it for today's lesson.